Hello, friends. This is Jim here with Science Talk, and I want to discuss with you a really fascinating study that just came out. And as you can see right here, the Arctic Ocean was covered by a shelf ice and filled with fresh water. And this is sciencebulletin.org / the Arctic Ocean was covered by shelf ice and filled with fresh water, all separated by hyphens. We go to sciencebulletin.org. So what are we talking about here? Well, you can see a bunch of diagrams here. I'll explain this at the end of what we're going to discuss here. I want to give you some background based on what's, you know, the verbiage that's here, and then we'll go back and explore this diagram further detail. What's happening here? Well, several scientists are now postulating that the Arctic Ocean was covered by up to a 900-meter thick shelf ice and that it was entirely filled with fresh water. This happened at least twice in the last 150,000 years. This is a surprising finding, nevertheless. It was reported in the latest issue of Nature. Is a result of long-term research by scientists from the Alfred Wegener Institute and Marum. So they did a detailed analysis of the composition of marine deposits. And by doing that, the scientists could demonstrate that the Arctic Ocean, as well as the Nordic seas, did not contain sea salt in at least two glacial periods. Instead, these oceans were filled with large amounts of fresh water under a thick ice shield. This water could then be released into the North Atlantic in very short periods of time, and each sudden freshwater input could explain rapid climate oscillations for which currently there's no satisfying explanation has been presented. About 60,000 to 70,000 years ago, a particularly cold period of the last glacial, large parts of northern Europe and North America were covered by ice sheets. European ice sheets span a distance of more than 5,000 kilometers from Ireland, Scotland, Scandinavia to the eastern rim of the Kara Sea. Kara Sea is, of course, in the Arctic Ocean. In North America, large parts of what is called Canada were buried under two very large ice sheets. Greenland, parts of the Bering Sea coastline were also glaciated. What was the ice situation like even further north in the Arctic Ocean? Was it covered by thick sea ice, or maybe perhaps you have tongues of those vast ice sheets from the continent were floating on the water, you know, towards maybe beyond the North Pole. And up to this research, and it's still hypothetical, but the way scientists answered these particular questions was pretty much hypothetical. In contrast to deposits on land, where you've got erratic boulders, moraines, glacial valleys, obvious signs that a glacier was in this vicinity once. Okay? Only few traces of vast ice sheets have been found so far in the Arctic Ocean. So the evidence is somewhat lacking. Geoscientists from the Alfred Wegener Institute, Helmholtz Center for Polar and Marine Research, AWI, and the Marum Center for Marine Environment Sciences at the University of Bremen have now compiled existing evidence from the Arctic Ocean and the Nordic seas, combined it with new data to arrive at the conclusion that we began this video presentation with. So, basically, over the past 150,000 years, the Arctic Ocean was filled with fresh water, is basically what it says. And it accumulated under the ice. So you had basically a big freshwater lake. These results mean a real change for understanding of the Arctic Ocean in glacial climates. To our knowledge, this is the first time that a complete freshening of the Arctic Ocean and the Nordic seas has been considered, happening not just once but twice, said the lead author and PI, Dr. Walter Gelbert, who's a geochemist at the Alfred Wegener Institute. So here's a little headline here. We're going to hit this in a moment. Thorium is absent in the sediment, so saline water must have also been absent. What are we getting at there? The finding is based on geological analyses of 10 sediment cores from different parts of the Arctic Ocean, the Fram Strait, and the Nordic Seas. The stacked deposits mirror the climate history of the past glacials. When investigating and comparing the sediment records, the geoscientists found an important indicator was missing, always in the same two intervals. In saline seawater, the decay of naturally occurring uranium always results in the production of the isotope thorium 230. This substance accumulates at the seafloor, where it remains detectable for a very long time due to its half-life of about 75,000 years. Therefore, geologists often use this thorium isotope as a natural clock. Here, its repeated and widespread absence is the giveaway that reveals to us what happened. According to our knowledge, the only reasonable explanation for this pattern is that the Arctic Ocean was filled with seawater twice in recent history in frozen and liquid form. Co-author, micropaleontologist Dr. Yuda Wallenberg, also from AWI, was said. So we have a new picture of the Arctic Ocean as emerging. How can a large ocean basin connected by several straits with the North Atlantic and the Pacific Ocean become entirely fresh? Such a scenario is perceivable if we realize that in glacial periods, global sea levels were up to 130 meters lower than today. And ice masses in the Arctic may have restricted ocean circulation even further. And that's a statement from co-author Professor uh, Rudiger Stein, also a geologist at AWI and the Marum. Shallow connectors like the Bering Strait or the sounds of the Canadian archipelago were above sea level at the time, cutting off the connection with the Pacific Ocean entirely. Right? You have Beringia, basically, and that's how it's thought that the first people came over. They walked across Beringia. In the Nordic Sea, large icebergs or ice sheets extending onto the seafloor restricted the exchange of water masses. The flow of glaciers, ice melts in summer, and rivers draining into the Arctic Ocean kept delivering large amounts of fresh water to the system. At least 1,200 cubic kilometers per year. A part of this amount would have been forced via the Nordic Seas through the very narrow, deeper connections in the Greenland, Scotland ridge into the North Atlantic, hindering saline water from penetrating further north. Basically, as we're going to see here, you have geological features that's served as a barrier for the salt water to move further north. Once the mechanism of ice barriers failed, heavier saline water could fill the Arctic Ocean again. We believe that it could then quickly displace the lighter fresh water, resulting in a sudden discharge of the accumulated amount of fresh water over the shallow southern boundary of the Nordic Seas, the Greenland Scotland Ridge, into the North Atlantic. A concept that assumes that enormous amounts of fresh water were stored in the Arctic Ocean and available for rapid release would help understanding the connection between a range of past climate fluctuations. It would also offer an explanation for some apparent discrepancies between different ways of reconstructing past sea levels. The remains of coral reefs have pointed to a somewhat higher sea level in certain cold periods than reconstructions from Antarctic ice cores or reconstructions from the calcareous shells of small marine organisms. If we now accept that fresh water may not only have been stored in solid form on ice, but some of it also in liquid form in the ocean, the different sea level reconstructions agree better, and we can reconcile the location of the coral reefs with calculations for the freshwater budget. Freshwater release from the Arctic Ocean might also serve as an explanation for some abrupt climate change events during the last glacial period. During such events, temperatures in Greenland could rise by 8 to 10 degrees Celsius within a few years, only returning to the original cold glacial temperature over the course of hundreds of thousands of years. We see an example here of a past Arctic climate tipping point of the Earth's system. Let me repeat that. We see an example here of a past Arctic climate tipping point of the Earth system. So let's see. So Professor Gelbert basically says we see the example of past Arctic climate tipping point, Earth system. Now we need to investigate in more detail how these processes were interconnected, evaluate how this new concept of the Arctic Ocean helps in closing further gaps in our knowledge, in particular in view of the risks of human-made climate change. Okay, so here's a description of the figure at the top. In glacial periods with low sea levels, exchange with the Pacific was halted, and exchange with the North Atlantic was extremely reduced. At the same time, the Arctic Basin was still receiving freshwater input. Exchange could occur only through narrow gateways in the Greenland Scotland Ridge. The sequence of three sketches shows one, a period of freshening of the Arctic Ocean, followed by two, the release of fresh water to the North Atlantic when the saline water enters the Arctic Ocean, and then three, a sudden melting of the Arctic ice sheet upon contact with the relatively warm and salty Atlantic water. Okay, so let's take a look at that. So we'll start with this general thing here. Here's your ice of about 900 meters thick, and it's like a lid on top of the entire thing. Here's Greenland, there's Iceland, here's Scotland, and these here are supposed to represent ridges, right? See, and these ridges serve as the gates. Now, sometimes it might be you can squeeze a little water, where there's some gaps in here, but this basically traps the salty water on this side of thing. Here's the Arctic Ocean. There's also, don't forget, the Lomonosov Ridge in the Arctic Ocean, which splits the Arctic Ocean into you got the Eurasian Basin and the Amerasian, or the American Basin. It basically splits that, and it kind of runs this way. So on this side is the American, that side is the Eurasian basins. And that comes up right now. Current levels is that the top of the ridge will be anywhere from about 400 to 900, 1,000 meters below sea surface. So if you've got the sea levels dropping 130 meters, and then you throw on a 900 meter thick ice cap, you could have the ice sitting right on top of the Lomonosov Ridge, and that's basically is a lid that really shuts things off. In addition to what we have going on here. Okay, so the first figure here, I want to hope that makes that a little larger to see. So what we see here is, you have the freshwater filling this up, so you got a freshening here. This greenish thing represents warm saline water. Blue is the uh, fresher water here. This white here is basically your ice sheet on top of it. Now it says here entrainment of remaining salt, basically pushing the salt out over onto this side here. So you have this. So by the time you establish this lid here, and you trap all the, you really separate the two. You have continuing input of fresh water from riverine, glacial melts, precipitation, that sort of stuff there. You basically have fresh water on this side here. At some point, okay, at some point, it starts to melt and the barrier breaks down, and you literally have the water spilling over the ridges. So it's now bringing, salt. The water is warmer, so you're going to bring in the warmer water as well. Now the salt, depending on the temperature, remember the TS curves, but typically, and I'm going to be doing a video segment on this. Typically, at least in the Atlantic side, yes, the water is warmer than the Arctic, but it has a higher enough sufficient salinity that it is denser. So even though it's warm, it still is going to be more dense than the cold fresh water, and it's going to sink. So it's going to spill over this ridge and start sinking. Well, it's bringing in warm water. That warm water is going to diffuse upward. And as it diffuses upward, it's going to start melting this ice. Now you get more of the ice melting away. Now the sea level starts to come up. Now you're just going to have this spillover, and you know, this denser water is now going to displace all this fresh water, moving it out. That's basically the mechanism here for what they're describing in this article. You basically shut off everything, so you don't have marine input into the Arctic Ocean. It's isolated. The fresh water builds up. It's basically like a big freshwater body. Then at some point, you get a little melting. You get some spillover. That salty water, it sinks, but also has heat that diffuses up, accelerates the melting. And now you've got this increase in sea level height. And now basically it's like the dam's been removed, and all this denser water just floods in, displaces the fresh water, and sends it out basically into the North Atlantic. And they say this has happened twice in the last 150,000 years. So this is a very interesting study. It basically sheds light, or at least provides an explanation for some mechanism that will control, what goes on in the North Atlantic, and thus what happens climatically, from a climatological aspect. Of very fascinating, very very fascinating, and they've done a very thorough job here, and it'll be interesting to see um, what further evidence and data they collect, and if this hypothesis bears out. Will we see such a thing soon here? Probably not, because sea levels are rising. Um, s- but it might explain what's happened in the past. And like anything else, if you want to know what's going on now, what might possibly happen in the future, take a look at the past. I hope you found this interesting. Thank you for your time.
Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.